I have forgotten to press the record button. Now we can also record. If I have overseen somebody of you, someone in the waiting room, just give me a hint. So the participant list is was, let's see. No, in the waiting room there is nobody at the moment. But in case you see and I don't, just give me a hint. Well, let's start. Um, have you been able to take a look on all the vocabularies we have had up to now, at least a short glance, so that I can use all that stuff? Oh, hey, there's a dot, and this dot is moving. Okay. Um, yeah. So that we can continue with the PN junction and all these calculations. Hey, it is not removing. I needed something which is wet, but it is the wrong side. I'm polishing. Okay, we will learn more about the PN junction by taking a closer look on all the charges we have in the space charge region. Before we have had the movement break, we have had this picture. This is the most important picture on semiconductors because all you can see here is one by one relevant for all semiconductor devices because you see here the band gap. Semiconductors have band gaps. The intrinsic level is in between of the band gap, roughly. Okay, so you have the so-called mathematically relevant Fermi level. What is the Fermi level? It represents the level at which half of the occupiable states are occupied. But here, no states are present, therefore, no carriers are present. But we have here a lot of carriers. How many? As many as you have implanted. Usually at room temperature, all are activated. You know this curvature, the reserve area, the exhausted area, and then the intrinsic area. So we are here where all implanted carriers are activated. So the thermal level represents this amount of carriers mathematically. And vice versa, if you have a lot of electrons, and if we put all these stuff together, diffusion takes place because here are a lot, here are the minority carriers, here are the majorities. So diffusion takes place, a recombination takes place. The recombination rate we have learned. If you have a certain injection rate, it adds an additional recombination rate. And if you recombine, you destroy these carriers and you leave back these ionized impurity centers. But they are not movable. They are there. The Poisson equations, they say all charges in an area represents a certain change in the potential, and the potential voltage times the charge is the energy. So the band bending is a result of these charges left back due to the diffusion entering combination. So this is qualitatively the status where we are now, today. Now we will take a closer look how we quantify all that stuff. At the same time, I said, if we are in equilibrium, what does that mean? If the drift, okay, the space charge does have a force of to the minorities in this direction and also for these minorities in this direction, but not if they are here, but if they are occasionally just here. So they are in the electric field, they drift in this direction, and here are so many, and here are no one in the easy way of saying. So they diffuse and drift back. So they diffuse and drift back, and some heavy energy particles, they diffuse and they are there. Okay, so the diffusion and the drift are in equilibrium. This is the thermodynamic equilibrium. In this state, the Fermi level is constant. So the Fermi level at the left side, the Fermi level at the right side, they are at the same energy level. This is a statement. The result is the distance of the Fermi level, of the original Fermi energy levels. This delta is now this band banding. This band edge banding has exactly this difference as a result, because now they're at the same energy level, but including the bending. Okay, so I think this statement, before we understand why and how, we should be also able to make a sketch. So we should be able to make a band sketch. So let's do that. Take a sheet of paper. I will do it also electronically. And we will start sketching a PN junction from the scratch. Okay? Step by step. So thereby, we concentrate we focus on the important points of a band diagram. The important point is first, where is the interface? Let's say this is the P type and this is the N type. Okay. Second, we have said that we have an abrupt junction. So the concentration in this area is constant for p-type, so boron, and the concentration here is constant, n-type, so phosphorus. And the switch is abrupt. This is the assumption. Okay. We know in the equilibrium, the Fermi level is constant. So we first sketch the Fermi level, E Fermi. For the N-type semiconductor, one moment. We know that due to the space charge, we have band bending. So we leave out a certain area for the band bending. So we don't sketch there at the moment, place our sketch at the moment. We do our sketch outside this area where the band edges are not banded. Okay, so for the N-type semiconductor, the conduction band edge is close to the Fermi level. Let's change the color. Let's make these band sketches red in my case. Okay, so this is the band edge of the conduction band for the N-type. Now we say, what type of semiconductor do we have? Silicon in our case. Therefore, we know the band gap. And the band gap is let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say 10 squares. Okay, so where we are? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares. So our band edge for the valence band is here. So we do that same procedure for the p-type. I have placed in the sketch the space charge region, the depletion region, symmetrically to the interface. That means the doping level is also equal. If the doping level is equal, the space charge penetration is equal. Okay. Why? Because overall we need to be neutral. If the concentration for the space charges here is this way, the concentration of the space charges here should be equal, because outside the space charge region we are neutral. Inside the space charge region we have one type of charges and this other type of charges, but overall we are neutral. Okay, so go on with the band diagram. We have here the distance which represents the doping level. So we sketch the same, roughly, it's a sketch, the same distance also here. So this is the valence band edge in the p-type semiconductor. And again, our band gap are 10 squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here we are up to the band depletion region boundary. So outside the depletion region, we have not banded band edges. Inside, we have the banding. How this banding looks like? The intrinsic, one moment. The intrinsic level is also in the center, in the first approximation. So let's sketch the center also. 1, 2, 3, 4, 5. So this is the center. And also here, 1, 2, 1, 2, 3, 4, 5. So this is the center. So this is the intrinsic energy level for both semiconductors. Let's start with the intrinsic one. The banding goes through the center and ends here. So we have the dashed line now. And we do the same roughly in parallel with the band edge of the conduction band. So we try to keep the distance constant. No, that was not very nice. So here, and no, I don't see the, no, I see it. Here, 1, 2, 3, 4, 5. So we do the same here and then same here, roughly. Okay, so now we have the band diagram of symmetrically doped, equally doped PN junction with no applied voltage. If you apply a voltage, you change something, but this will come later. Now let's take a look why and how this band diagram looks like it is presented here. First, just do this correction. Uh, Diffusion constant I have written, it is a diffusion coefficient. So please do this correction here, diffusion coefficient. I stated that the Fermi energy level is constant. What does mean mathematically constant? Constant means that the Fermi level is a function of the x direction, the the derivative for x is 0. Okay, now let's take a look here how we can find that out. So this is the result we would like to have. We take the convection current density. What is the convection current density for electrons? It is the movement of the charges due to the electric field and the movement of the charges due to diffusion. And what we have learned in the equilibrium, that the sum of these movements is 0. Okay, so the convection current density is 0. Well, now let's put in from the Poisson equations that the electric field is minus the first derivative of the potential. You remember? If you have an electric field for a plate capacitor, so here 0 volt, 10 volt, then in between you have the potential. Here is the potential 0, here is the potential 10, and here in between it is the potential 5. So your potential is changing. But the electric field in between is constant for a plate capacitor. So if you have an electric field, you have a changing potential. Just to repeat in a very simplistic way this statement. So we put this equation here in. Second, we know that the carrier density, the movable carriers, can be expressed, this concentration, by the intrinsic concentration times e to the power of Fermi level minus intrinsic level. You remember where we have had this equation in our lectures? It was some years ago. Here. Here you have this statement at this location. So if you take this equation and take the intrinsic concentration out, then you end up at the equation I have just used on page 47. Okay, so we put in here, and the diffusion coefficient we also know, we put in here. And then we end up having this one and this one. What is the intrinsic energy, the equation for the intrinsic energy level? It is a certain level and it changes with the location. So we put in this equation also here. And if we do these derivatives, we end up that this value, one moment, this value is equal to this term. You see, if you put in here and you calculate the first derivative, you have this term and this term with the first derivative. And this is 0 after the first derivative. Okay, so you have at here and here exactly the same stuff except this additional term. And this additional expression needs to be 0 if your convection current density is 0. So mathematically, it turns out that the Fermi level needs to be constant if your convection current is 0. This is a mathematically precondition. And this precondition I have taken to this slide and said, okay, the Fermi level is constant. But I am lying a little bit at that point because Fermi level is relevant where you have your charges. But here in between, we have moving concentrations as moving charge carriers and changing concentrations. So you don't have this concentration also here. You don't have that. Therefore, this line is an error, is false. This line is just for my laziness to draw one line. Okay? So keep in mind that you should delete this line, but in order to state that it is constant, I have one line through all the regions. Okay? In literature, you have in the depletion region, in the space charge region, so-called quasi-Fermi levels. But we don't take a closer look to the quasi-Fermi levels. We keep up just with the Fermi levels themselves. Okay. Now let's continue. We want potential at the p-n junction. We want to calculate this stuff. I said that the so-called band bending is the original difference in the Fermi energy levels. And we know all equations about these Fermi levels. Also on the page, I think 48. So I have copied these equations from this table and inserted them into this equation after the division of Q. So we have the built-in voltage at the left-hand side and Fermi level of the n-type minus Fermi level of the p-type divided by Q. And if I calculate that equation, if I not calculate that equation, how you say it? Not calculate, calculate that equation. Rearrange your equation. Thank you very much. Yes. Mr. Botta, you are my dictionary. Great. Then we end up having Boltzmann constant times the absolute temperature divided by Q. That's here. Here you can say it is V temperature times the natural logarithm of what is the here nd times na divided by ni, but square. So this equation I have also in the spreadsheet. Please open the spreadsheet. You see, I have prepared also a scene in the OBS studio so that I just click here, I have my iPad, and just click here, and then I have my spreadsheet without all the fancy infinity windows we have had originally. Okay, I have done it after I have made my coffee this morning. Okay, so let's take a look to the spreadsheet. So the thermal level distance to the band edge calculations are here. So it's an electron volt. The doping concentrations are here. 2 times 10 to the power of 16 I have chosen to be the doping concentration. And the temperature voltage, yeah, for how warm weathers for 300 Kelvin, you see here. Can you see my mouse? No, you can't see my mouse. Or can you see my mouse here? Ah, okay. So I have to place my cursor on the Excel. Then I have to go to the presentation. Then you can have my mouse. Okay, the absolute temperature, 300 Kelvin. Now let's see. Here we have our built-in voltage, the equation I have copied here. And if we calculate the built-in voltage using the temperature voltage, doping concentrations, and the intrinsic carrier concentration, we end up having 0.731 volt. This voltage you can't measure outside the diode. This voltage represents, now I'm switching back to my slides. I love it. Represents just this banding caused by the space charges here and here, axis here and here. Okay. But occasionally, not not very much occasionally, but it is roughly the voltage you have in mind for silicon in forward bias condition. You will learn that this voltage has something to do with this forward bias you have in mind, but it is not exactly this value. Okay, but keep in mind. So I have some calculations here. I think we don't have to do that, but because we have our spreadsheet, the temperature voltage, how we do the calculation, it is KB, so 1.38 times 10 to the power of 23 joule per Kelvin times 300 Kelvin times 1.6 times to 10 to the power of minus 19 coulomb. Now I don't see any voltage because we should end up at voltage. So let's take a look at the units of this equation. So joule is volt ampere second. Kelvin divided by Kelvin times Coulomb is ampere second. So now you can have the required unit out of this equation. It is a voltage. This is the only reason why I have put in here this calculation area. And the built-in voltage we should uh, really calculate with these values here. So the built-in voltage is the temperature voltage. We take the value out of the spreadsheet times the natural logarithm of Na, 10 to the power of 16, times Nd, 2 times 10 to the power of 16, divided by 1.5 times 10 to the power of 10 square. And we have had 2 times cubic centimeter, and also due to the square, 2 times cubic centimeter in the denominator of the denominator. So we have it here at the, what is the Zähler nominator or numerator? Thank you. Numerator and denominator. Numerator. Thank you. Hey, you deserve a present. Thank you very much. So at the end, we have a factor in the natural logarithm. Ah, Mrs. Surden is waiting. I put it into our group. I have just seen a message from her. Okay. So, hello, Mrs. Sudenis. I have just taken my mobile phone to make some calculations, and then I have seen that I have missed your request for entering the room. Hi. Okay, so I have had the participants list just 5 minutes after the start in my vision, and after that, I haven't had this participants list in my focus. So I'm sorry for not having seen you. Ah, okay. They're always late. Okay, I have to shoot up the lecturer. Okay, so um, just let my phone ring with WhatsApp. So it is vibrating all the time, so my focus is derived to my phone. Okay, so sorry for letting you waiting outside. Um, I'm just trying to calculate this equation by using my fancy pocket calculator. And it comes out that this natural logarithm, this value is 27.5. And this VT is 25.9 millivolt. So I have taken the value from here. Now switch back to the iPad. And then we have, if we multiply, thank you very much. So the so-called built-in voltage is 0.713. Again, it is not the forward voltage of the diode, but it has something to do with that value. Okay, now let's continue. Why we have the bending like we have? In the sketch, we have had all this stuff, and we said, let's bend. Now, let's calculate. First, the depletion region has a box-shaped doping level. In the n-type semiconductor, the charges in the space are positive. Therefore, we have here this line, and it is constant as a function of the x direction, x value. In the p-type area, the space charges are negative because they have accepted the electron. Okay, so therefore we have this line at the negative axis of the space charge, y-axis. And it is again constant because we said it is constant. And outside the space charge region, we have no charges because it's neutral. Okay. And what we know is if one concentration is different to the other concentration, then the space charge region penetration into the semiconductor from the interface is also different. Why? Overall, we need to be neutral. So if one concentration is higher, then the space charge penetration is shorter. But how short? We don't know. But it is shorter. But the relation of these boundaries is given by this equation. And in this case, our n-type is twice as high doped compared to the p-type region. Therefore, the space charge boundary is 2 times far away from the junction as for the n-type. So this is the situation we have, but we don't know whether this boundary is this and that long or this and that long. We don't know that at the moment. We don't just know this equation. Okay, let's go. Let's fix these boundaries. For x areas at the left-hand side of the space charge region boundary, we are neutral. This word neutral means no space charges. So this is one line. Second line. Inside of the space charge region, but at the left-hand side, we have a certain value of the space charge. This is this line. And the same game at the right-hand side, we have also a constant space charge, namely this value. Okay, what does the first integration delivers us? Okay, we have now the space charge. The first integration delivers the electric field. Okay, so let's integrate. Constant integration of a constant is easy. So if we take into account the boundary conditions, the first integration says that the electric field does change constantly. Yeah, sure. A constant integrated delivers a constant slope. Okay, so that means if we fix at the boundaries that the electric field is zero, Then the mathematics says that this slope is proportional to this constant. Yeah, sure. And if we have a higher constant, which we integrate, we have a higher slope. A positive value gives a positive slope, a negative value gives us a negative slope. Yeah, mathematics in the first semester. But what does that mean? This means that the electric field is maximum as an absolute value at just the interface. This is a very important statement. If you have a diode, the electric field is in the center maximum. Now, oh, okay, I will state that later. We can calculate this electric field by, yeah, we know this doping level, we know perhaps this space charge boundary position, and we can calculate it from left or from right. It ends up at the same point. Okay, let's go back to the spreadsheet. In the spreadsheet, we see this equation. Okay, I have to zoom out to have a certain overview. Uh, I haven't done that immediately because due to the spreadsheet size, my spreadsheet for Mac has requires some seconds or minutes to do that. Now we have it here. Where we see this energy. Here we have. Okay, so we have here the PN diode. Okay, we apply no voltage. So I click here. 1, 2. So to explain it, this value is the voltage in front of the comma. This point is the first position after the comma. So it is now 0.0 volt. Okay, and if I do that, I have with these given concentrations, let's type in also the concentrations uh, of our lecture. We have 2 times 10 to the power of 16 at the right hand side, but 1 times 10 to the power of 16 at the left hand side. And if we do that, if you give in these values, we should see exactly this one. You see? Constant value at 1, constant value at 2, and the space charge boundaries are also sketched into this Excel diagram. Okay, now let's see this first equation we have gained by the integration. You see that here we have the negative slope, the positive slope, we have this maximum energy level, electric field level, and here it is calculated here immediately. And it has a value of 3.8 times 10 to the power of 4 volts per centimeter, just as a value. The maximum breakdown electric field in silicon is 3 times 10 to the power of 5. So we are far away from breaking down in silicon. Okay? So this you have to take into account. Oh, one more person is in the waiting room. Mr. Hussein. So you were very fast, Mrs. Akbal. Okay, so let's go back to the iPad. Tuck. Here we are. You see, I have just copy pasted from my Excel sheet all these diagrams. I haven't painted it by hand, except except there are straight lines. Now, let's go back to the Poisson equation. What we get if we integrate again, we get the potential. Okay, so now I define the center that the potential is zero. And after the integration of a constant slope is a square, 2 to the, no, not square type slope. Okay? Yeah, yeah. Se Second order of quadratic. I just looked for quadratic. Yeah, quadratic slope. Okay, thank you very much. Um, Now we have the quadratic. So x to the power of 1, x to the power of 2. Well, at the left-hand side we are negative, at the right-hand side we are positive due to the space charges. So this is the initial point. Then you see that the potentials are like this. And at the space charge boundary, we have a certain value. So at the space charge boundary, this value is this value, but with a negative sign. So this part of this equation is zero, and we end up having this part of this equation here. And the same applies to the n-type. The variable part is zero at the boundary, and we end up having the constant part. So these values, I think I have also calculated in the spreadsheet. Let's take a look. Yeah, here we are. And you see here the potential within the diet. We set the center to the zero, and we have then this banding. If you have taken a closer look to the potentials and the band bending, you see something which is similar. It is this one. The band bending is exactly what we have from the potential in the space charge region, because the energy is just the potential times Q. That's it. Therefore, I have written once this. So the potential times Q is the energy. And all these graphs in my lectures you see here are a copy from the Excel calculation. So these bendings you see here are not sketched by Excel. It is plotted by Excel and pasted into PowerPoint. Okay. Why I'm saying that? In some literatures, you see very weird band bending sketches. So take the spreadsheet and do the calculations yourself. So you see the real banding in a semiconductor. And why I have done that? I was very thrilled to see how it should look in the real life because box-shaped bending is not by definition correct, and nobody has shown me in the former time the real bending. And after I have seen this calculation, I said, "Ah, yeah, sure, okay, I have just to copy and paste it to my band diagram. That's it." Okay, so we have the quantitative analysis of the PN junction for this condition in the slides and also in the spreadsheet. Okay, so take always the spreadsheet to verify your knowledge. Now let's come back to the point where I have said we know that the space charge ends somewhere, but we don't know what is the extent of this phase charge region, extension of this phase charge region. To be able to calculate this value, we need not very much new stuff. We have to rearrange all Newton equations. First, we need to know the built-in voltage. Yeah, we have calculated that. What is the built-in voltage? Yeah, the built-in voltage is this. Yeah, band bending, you know, from the beginning. So the band bending, just to repeat, just to have this in front of you, the distance in the Fermi level is now this bending, and this bending is except from Q, the built-in voltage. Okay, and now we have the built-in voltage by equation. It's namely this minus this. Well, here we are, built-in voltage. Then we know that the potential at the boundaries have these values. Okay, and we know that this relation needs to be kept constant. Well, okay, if we use all these equations, we can calculate the penetration of the space charge region into the P zone and into the N zone. And we see due to the second integration of the constant space charge, again, due to the second integration of this constant charge in the space, we have the quadratic behavior. And due to this behavior, we have a square root dependence on the voltage. Okay, so the space charge boundary is a function of the built-in voltage, is a function of the doping levels, and the overall space charge is the sum of them. Well, now let's take a look what happens if one side is doped heavily. If one side is doped heavily, then we have, if this goes, for instance, if this goes to infinity, and this goes to infinity, then you can take out this plus small value. And then this one goes out to be 1. So if the N-type region is doped heavily, we have just a penetration into the P-type only dependent on its own doping level. If your dopings are not heavily different, then the penetration into one direction is also dependent from the doping level of the other direction. Okay, and vice versa. If your doping concentration in the p-type goes to infinity, then sorry, here, then the small plus nd is not relevant. Here we get 1, and then the penetration into the N zone is just dependent from the doping level of the donors. Yeah. Overall, we should take a look here. It's like a parallel connection of two resistors, if you take a look to this equation. But again, okay, Mr. Sulak. Yeah, hello, Mr. Sulak. Sorry for having waiting you outside. Oh, you haven't been able to enter the room. I have put you, I have given you the allowance to enter the room, but it hasn't worked the last time, right? Oh, okay, okay, okay. Oh, so fortunately, we are recording all that stuff so that entering, not entering doesn't hurt so much. It hurts, sure, but not so much. Okay, hello. So the overall space charge region extension is dependent from a square root. So take this with you. That's the takeaway from these calculations. The space charge region has a square root dependence to the voltage. We will need that later. Okay, let's continue. What happens if we apply voltage? First, reverse bias. If we reverse bias, we are not in steady state. So this diagram is not in steady state. I just want to give you yeah, an heuristic explanation. What happens? The heuristic explanation is if you have your if you apply a positive voltage at the right hand side, the negative voltage to the left hand side. So if you apply negative pole to the P zone and the positive pole to the N zone, your diode is reverse biased. Why? You attract, so F is the force. You attract the mobile charges, these carriers, to these poles. So the mobile carriers are attracted towards the poles. So this is the easy way, so kindergarten way of talking about what happens. And this attraction causes the increase in the space charge. And the result is the space charge region has increased. And what has happened? You have perhaps here two more charges, which cause more bending. What does more charges, and thereby after 2 times integration we have this bending, you know? This additional bending causes the separation of the Fermi levels. This separation represents your applied voltage. Again, your applied voltage increases the space charge region. The space charge region increase has caused bending. additional banding. This additional banding separates your Fermi levels, and the separation value is exactly your applied voltage. Now, let's go away from talking about forces. What is voltage? Voltage is a potential difference. A neutral area can't absorb a potential because it's neutral. The only area which absorbs a potential is where you have charges. So the space charge absorbs your applied voltage. So if you take your PN diode, you apply a voltage across the PN diode, only the space charge absorbs the applied voltage, nothing else. These are neutral. Now let's go back to the spreadsheet. Okay, so let's zoom in here a little bit. One more. Okay, so that's enough. It takes too long. So if now we apply a reverse bias, I click down here, minus, let's say 1 volt. No, I have made it different way. The first digit, it is not very intuitive. The first digit represents a negative voltage. Okay, so if the first digit, if we give there a value, 2 volt, it represents a negative applied voltage. Okay, so if you see clicking here down, we get 0. I have just clicked here on the spreadsheet. One moment, once again. So we have the equilibrium, and if I click at the up arrow, we apply 1, 2 volts negative voltage. So the space charge region increases, and you see that the electric field also increases for sure. And your band bending, the potential as a function of the location, also changes with the extension of the space charge. Okay. And this change, I go back to 0 volt. So this is the 0 volt condition. This change in space charge region extension is the reason of your applied negative voltage to the diode. What happens now if you further increase the reverse bias condition? Let's take a look at the electric field. Now I have doesn't work here. Perhaps here. Okay, I have limited the value to 5. Okay, because for values higher than 5, we are out of the scale. That's the only reason. The electrical field at the space charge boundary is now 1 times 1.1 10 times to the power of 5. Remember, The critical electric field in the silicon for breaking down is now not very much far away, 3 to 1. That means if you design a diet with these doping levels, with these doping levels, then this diet breaks down at, let's say, 6 or 7 volts. And vice versa. If you want to design a diet which breaks down at 600 volts, you know now that you have to dope the semiconductor very low. This is the consequence. Low doping means what happens if we want to let flow the current through the diet. One moment. If you have, if the current flows through the diet, this area, one moment, this area and this area are both neutral. So these are the parasitic resistors. So if you want to have a high voltage silicon diet, you have to dope it low. You have to have a large space charge region. And if you want to operate this diet, then you have a large area where the parasitic resistance is very high. So you need a large area where the current flows through the wafer. Therefore, high voltage devices are large area devices due to the high parasitics you have in these devices. So what we have learned from these, from 2 times integration, we have learned that we have a band bending. We have learned that we have a band bending, and we have learned that also we have in this space charge the absorption of your applied voltage. Let's take a look here. So additional negative voltage increases the space charge region boundaries. Therefore, it increases, you see, the slope hasn't changed because your doping level is constant. But the integration path has been increased, so therefore the maximum electric field has increased in an absolute manner. And so you have now the built-in voltage minus the applied voltage. Why minus? Because V itself is negative voltage. So minus gives plus here. Yeah. So don't be disturbed from this minus sign. Negative voltage. Okay. Now let's go. Yeah. Now I have a problem. A problem. I want to give you a problem. If I apply a negative voltage, the space charge boundaries does penetrate into the neutral area, the width increases. And I said your applied voltage is absorbed in this at this distance. So why does a diet break down? Because you increase the applied voltage, you increase the space charge region. So the electric field isn't changed, but obviously it is changed. So what is my problem in my thinking? Mr. Muka, this is a design, uh, not issue design value, which you have to take into account. Basically, you're right, but although you have designed the diet large enough, this diet will break. Why? So you have enough space for the space charge. Why? Why is the electric field increasing? So mathematically, sure, it increases. We have seen that. But I'm looking now at this part, this part, and say V increases if I increase the reverse bias. Why is the electric field increasing? Because electric field is voltage per distance, and this distance is increasing. Yes, but how? Yes, exactly. You have it. This is the reason. The the square law. So the space charge region increases as a function under the square root. So if you increase this voltage, you don't. So doubling the voltage is not doubling the width. Therefore, the electric field, like it is obvious, is increasing. This is the reason. That means you increase the voltage. The space charge region is also increasing, but not at the same value because of the square root. That's all. Due to this fact, the diet is breaking down. Also, you have enough room to increase the space charge region. Okay, so take this into account. If you this yes, drift current. That's the point for the drift current. I will come in 1 second. One, two, three, four. In these areas, 4 to 5 slides, we will get a very close look to these currents, and then we will see very interesting topics about this drift and diffusion stuff. But hold on this question to the later slides, Mr. Vuka. Thank you. So now let's go to the uh, no, I haven't updated my my headline. I've just copied it as I see here. Okay, the numbers, forget about the number. It is now forward bias. Okay, forward, forward, larger than zero. Okay, so now we talk about the forward bias. The forward bias is the bias voltage positive, and the definition of the positive voltage is P to N region, this voltage from P to N. So from the P region to the N region, we have a positive voltage. Okay, Um, by means of remembering it by simplistic values, p-type positive, n-type negative. Okay, so again, we can say we just push the electrons, the charges, into these areas. Yes, we do. But the applied voltage is again absorbed in the space charge. Now, what you see, the space charge region is reduced. So this change, the left side, the P area was up. Now the P area is down. Okay, now you are counteracting the electric field in your space charge. You counteract, so you collapse the space charge region. So if you reduce the space charge region, now we can talk about why a diode does have a current. If you reduce it, your bending is reduced. If the bending is reduced, your barrier for the electrons is reduced. What happens if you have a swimming pool and you push down the one side of the swimming pool, which is large? The water is pouring out. And this happens here. Higher energy, more electrons are now available, which have enough energy. So Fermi-Dirac statistics, higher energy levels are occupied. But if you don't have to rely on only these values, but also to these values, you have more of them. So these electrons can diffuse and recombine. So a PN diode is a diffusion device. It relies on diffusion. And then after the diffusion, the recombination takes place, which makes the current. Okay, so less electrons bounce back in the electric field, more electrons diffuse. Now, Mr. Mukha, I have one more idea which I can explain to you all based on your question, Mr. Mukha, for the reverse bias. This is again, we switch back to reverse bias. We have now more space charge region, a wider space charge region. And you see here, do you have any electrons which have enough energy in this sketch? Enough energy which can diffuse? No. But the minority carriers we have. That means the minority carriers, if they by occasion enters the space charge region, drifts to the other side. But no diffusion back does occur. That means if you reverse bias a PN diode, you have the minority carriers which contribute to a recombination. This means you can't avoid a reverse current in diode. It is a function of the minority carriers in the device. You know? Okay. That means In reverse direction, we have a current, but as we know, the minorities, the name gives us the value, it is very low. We have a very low current, and vice versa. If we have a forward bias, one moment, the Boltzmann approximation. What is the change in the concentration as a function of the energy in the Boltzmann approximation? Again, the question. What is the change in the concentration as a function of the energy level in the Boltzmann approximation? What is this distribution? What dependence does it have? It has at the intrinsic level, for instance, times e to the power of, let's go to the table where we have this equation. Here we are. So here we switched, one moment. Here we switched from the Fermi-Dirac to the Boltzmann approximation. From this Boltzmann approximation, we derived at the end, one moment, for electrons, this equation. And if you take a closer look to this equation, or if we have it here, so the location-based concentration is exponential. So if we are, so as far as we go away from the intrinsic level, we increase the intrinsic concentration exponentially. The exponential equation we have written down during the calculation of the Fermi level. Let's go to the calculation of the Fermi level. Here we are. So exponentially, your carrier concentration increases if you increase the energy level where you are. Okay, so if we take this exponential increase of concentration into account, this is now the important point. So if we take, this is the intrinsic level, and all the positions you go here, you increase the concentration exponentially. And this means if you reduce your space charge, if you reduce your barrier, the amount of electrons increase exponentially. Therefore, the diode current is exponential to the applied voltage. But this calculation we will do later, so 4 or 5 slides later. At this point, you can already see this by having the Boltzmann approximation in mind. The Boltzmann approximation says the concentration increases exponentially as a function of the energy, or reduces. By increasing the energy, the concentration is reduced, or vice versa, reducing the energy, the concentration is increased. So in reducing the barrier, you have to overcome, you increase the amount which are available for diffusion, increases exponentially. So this is for you, Mr. Buka, for your question. Okay? The quantitative answer to your question will come later. But first we have to see these balls in the air. The electrons. Okay. Um, well, let's say we make here a break and we'll see us in the afternoon. Let's say 2 o'clock is okay. Let's see us at 2 o'clock. See you later. Okay, alles klar. Ja, ja. All is recorded, so Mr. Müller, schön, don't worry. Um, and just gather your questions so you can drop it the next time. See you. Bye bye. See you next week. Okie dokie.